Lecture 22, Catalysts and Radioactive Decay. The last topic that we need to discuss in regards to chemical kinetics are catalysts. So catalysts are chemical species that are added to increase the rate of reaction. Catalysts usually increase the rate of reaction by changing the mechanism of the reaction. The new mechanism oftentimes has a lower activation energy for its rate determining step than the activation energy for the previous reaction. For the reaction profile on the right shows a catalyzed versus an uncatalyzed reaction. The non-catalyzed reaction is a one-step process and has one activation energy. The catalyzed pathway, which is shown in red, is now a two-step process with two activation energies. The activation energy for the slow step, or the first step, is a lot lower than the activation energy in the original reaction profile. Catalysts typically participate in a reaction since it changes its mechanism, but are not consumed by the reaction. This means that you start with the catalyst and end with the catalyst. Note that this is opposite of the behavior of a reactive intermediate, which is formed in the process of the mechanism and then is used up. Catalysts are used up and then reformed. We typically represent catalysts by placing them above the reaction arrow for a chemical reaction equation, as shown on the right. There are many types of catalysts, but we'll discuss three here. Homogeneous catalysts are catalysts that have the same phase as the reactants in a given reaction. For example, if you do a reaction in aqueous solution, and you add another aqueous solution that serves as the catalyst, then this is an example of homogeneous catalysis. You can also have heterogeneous catalysis where the catalyst has a different phase than the rest of the reaction. Here's an example of a heterogeneous catalysis. You have the gas phase reaction that shows the decomposition of NH3 into nitrogen and hydrogen molecules. This reaction is catalyzed on a surface of platinum metal. The NH3 molecules absorb onto the surface of the metal, where they're held there so that they can rearrange to form the products, which are then expelled from the surface of the metal. There are also biological catalysts called enzymes. Enzymes are typically proteins that are able to hold reactants in a certain configuration that allow for reaction to occur. Here's a simple example of how an enzyme works. The enzyme, which is the blue blob on the screen, has an active site where the substrate or reactants can connect to. Once the enzyme binds to the substrate, it holds the substrate there so that the reaction can take place and then expels the products. This is very similar to the heterogeneous catalysis. This ends our unit on chemical kinetics. We're now going to shift gears and start talking about nuclear chemistry. we will actually revisit some aspects of kinetics as we talk about the kinetics of radioactive decay and its application to radioactive dating. So far, we've looked at chemical reactions, where we rearrange atoms to form new products. Chemical reactions are driven by electrons. In all chemical reactions, electrons are either transferred from one species to another, or they're rearranged as new bonds form between molecules, between atoms in new molecules. Therefore, we can change different substances or different compounds into other compounds through the work of chemistry. But what if we want to make a nuclear change? That is, what if we want to change one element into a new element? Remember from Gen Chem 1 that the identity of an element is determined by the number of protons in its nucleus. So to change the identity of an element, we must change the number of protons in the nucleus. This can occur because of the natural process of radioactive decay or through nuclear bombardment reactions in cyclotrons in nuclear facilities. So when we look at nuclear chemistry, we're really going to look at the transformations of nuclei, either through natural processes or man-made processes. One skill that we're going to need in this unit is to be able to write equations for nuclear reactions. We'll do this by writing nuclear equations, which show the transformations between nuclei during the process of a nuclear reaction. In a nuclear equation, we use nucleide symbols to represent the nuclei that are undergoing the changes. Remember from Gen Chem 1 that a nucleide symbol shows the atomic symbol for the element, which is the X here, with a subscript to the right of the atomic symbol that represents the atomic number Z, or the number of protons in the nucleus. The superscript to the left of the nucleide symbol is the mass number. The mass number is the sum of the number of protons and the number of neutrons in the nucleus. We can also write nucleide symbols for common particles that may show up in different reactions. For a proton, we use the symbol a lowercase p for protons. The mass number for a proton is always going to be 1. Since the proton is a subatomic particle, instead of using an atomic number, we actually use the charge on the particle. Since protons have a positive 1 charge, we use a 1 as the atomic number. You can also note that protons protons might show up as hydrogen atoms as well, since hydrogen atoms typically have 1 proton. Neutrons are given the symbol lowercase n and also have a mass number of 1, but have an atomic number of 0, since neutrons have no charge. For the electron, we use a lowercase e. Since the electrons have a very small mass relative to protons and neutrons, we give it a mass number of 0. The atomic number, or the charge on the electron, is going to be a -1. Another particle that we'll encounter a lot in this chapter is the positron. The positron is the antimatter counterpart of the electron. If you're not sure what antimatter is has all the same properties of regular matter, except all the charges are reversed. Therefore, an anti-electron would have a positive charge because electrons have a negative charge. In this unit, we'll give the positron a symbol of a lowercase e symbol with a line on top of it. The mass number for the positron is also 0, but the charge on the positron is a +1. To use nuclei symbols to write a chemical equation, we can remember one simple rule: that the sum of the mass numbers and the sum of the atomic numbers on both sides of the equation must equal one another. If we look at the example on the top, which is the alpha decay of uranium, we see that the mass numbers on the product side, 234 plus 4, add up to 238, which is the mass number for uranium. The same is true for the atomic numbers. 90 plus 2 equals 92, which is the mass number on uranium. The first thing we'll look at in this unit is natural radioactivity, or radioactive decay, which was discovered by Henry Becquerel in 1896 as he studied photographic plates. He wrapped a sample of uranium up and stored it in a drawer with his photographic plates, and discovered an image of the wrapped package on the photographic plates a day later, and noted that in the dark drawer, the photographic plates were not exposed to light, but were exposed to the natural radiation that came from the uranium sample. Radioactive decay is the emission of subatomic particles or electromagnetic radiation that come from a sample or an atom undergoing some transformation. In the next few slides, we'll look at different types of radioactive decay and what kinds of transformations of the nuclei have to occur to have them happen. The first type of radioactive decay is alpha decay. Alpha decay is the emission of a helium nucleus from a high mass nucleus. The helium nucleus is a very stable nucleus, which is why it is often emitted during radioactive decay. The example we showed when we took a look at nuclear equations is an example of alpha decay. In that example, uranium, which is a very massive atom, undergoes a transformation where a helium nucleus is actually emitted from the uranium nucleus. This leaves behind an atom that is now thorium-234. We call this helium nucleus an alpha particle. Remember that helium has an atomic number of 2, which means a helium nucleus has a +2 charge and a mass number of 4. So we now have a high mass, highly charged nuclear particle heading out at a pretty high speed. Since alpha particles have a pretty high charge magnitude, They have a high ionizing power, meaning that they can cause damage to biological tissues through ionization or taking electrons from them. However, since alpha particles are rather big, they can't penetrate very well through different barriers. You can stop alpha particles, for example, by using a simple shield made from a piece of paper. And human skin is a very good barrier from alpha particles. The next type of radioactive decay is beta decay. Beta decay occurs when a neutron is converted into a proton and electron. The proton stays embedded in the nucleus, converting the nucleus into a new element, while the high energy electron leaves the nucleus. We can call these high powered electrons beta particles. In the example, we look at the beta decay of carbon-14, a very common radioactive isotope used for dating. Carbon-14, when carbon-14 undergoes beta decay, it forms a neutron plus a beta particle. It forms nitrogen plus a beta particle. Sorry about that. Electrons have a lower charge magnitude, -1, 1 instead of 2, than an alpha particle. They are also less massive. This affects the type of damage it can do. Beta particles can do less ionizing damage to biological tissues because of the lower charge magnitude. However, since electrons are more massive and are traveling at a higher speed, they can actually penetrate through barriers. A simple sheet of paper or human skin will not stop a beta particle. However, you will start to need a thin layer of lead shielding. The third type of radioactive decay is gamma emission. Gamma emission is the emission of a high energy photon from an excited state nucleus. The highest energy photon would be for gamma radiation. Gamma emission occurs usually when a nucleus is in an excited state and relaxes down to its ground state. The nucleus might be in an excited state because it just undergone some sort of radioactive decay. For example, in our uranium alpha decay example, the thorium atom can end up having extra energy after the radioactive decay process. Therefore, when that excited state nucleus falls down to a lower energy state, or the ground state, it gives off that extra energy as a photon of light. Gamma radiation has the lowest ionization power since photons do not have a charge. However, since photons do not have a rest mass, they can penetrate through many layers. Heavy lead shielding is needed to protect from gamma emission. Another type of emission is called positron emission. So this is the emission of a positron when a proton is converted into a neutron. An example here is the isotope carbon-10 undergoing positron emission. As a proton is converted into a neutron, you form a boron nucleus and a positron. The other particle that's formed during positron emission is a neutrino. We won't worry too much about neutrinos in chemistry. However, just as a public service announcement, neutrinos are particles that are generally emitted during many radioactive processes, including the fusion reactions that take place in the sun. Many millions of neutrinos are radiated on the Earth every second. However, since neutrinos do not interact with many particles, we don't feel their effects. It takes special equipment and special experiments to actually detect the neutrino. Since positrons have the same mass and charge magnitude as electrons, they have the same ionizing power and penetration power as beta particles. The last type of radioactive decay is electron capture. Electron capture is a pretty rare process, but has the same effect as positron emission. That is, a proton is converted into a neutron. What happens in electron capture is that an inner core electron, or 1s electron, is absorbed into the nucleus and combines with a proton to form a neutron. This leaves a hole in the inner shell of the atom, as shown on the right for fluorine undergoing electron capture. This hole is immediately occupied by a higher energy electron. As that electron moves into the lower energy state, an X-ray is given off. And this is usually how we tell that electron capture has occurred, through the emission of X-rays. Notice that the electron in the nuclear equation appears on the left-hand side or reactant side of the equation. We also get neutrino emission in this reaction too. Note that electron capture is a pretty rare process and only certain nuclei will undergo it.